We're continuing on physical chemistry. We're beginning chapter 2 with section 1. We're going to talk about the first law of thermodynamics. Mechanics has three categories. The first is classical mechanics. This is the same as Newtonian mechanics. This applies only to macroscopic particles or macroscopic objects. This applies also when your velocity, this is lowercase v, is much less than the speed of light. Lowercase c is the speed of light. When you have two arrows, less than arrows like this means much less. The second type of mechanics is relativistic mechanics. Now this will apply to both macroscopic and microscopic particles. This applies when the velocity is close to the speed of light. Remember, this wavy equal sign means roughly equal to, or approximately equal to. The third type of mechanics is quantum mechanics. This applies to microscopic particles. And this applies when the velocity, that's supposed to be a lowercase v, is roughly equal to the speed of light. Now thermodynamics, that's what we're going to be talking about quite a bit, uses classical mechanics. Now remember Newton's second law of motion. Remember physics with calculus is a prerequisite for this, so hopefully you already remember this. Force is equal to mass times acceleration. Now this arrow means a vector. So mass doesn't have the vector sign, so mass is a scalar. This a, lowercase a for acceleration, this has the arrow, so that means it's a vector. And this capital F for force, this has the arrow over it, so that means it's a vector. So force and acceleration are both vectors, and mass is a scalar. Now the total force is equal to the sum of the vector forces. So we're going to use subscript I to when we count through more than one, force 1, force 2, force 3, etc. So we take all these individual forces. This probably should be seen as a vector. Anyway, so you add up each force vector, vector 1, 2, 3. This epsilon means sum. So the total, like I said, this total force vector is equal to the sum of the individual force vectors. For example, here's some coordinates in x, y, and z, and then we have a mass m up here. Its distance to the origin, denoted r, that's easy to remember because you could think of it as the radius, but we're not talking about a circle. It's actually the total displacement, so we call that the displacement vector. And of course, with magnitude and direction, that would be a vector. This doesn't have a vector sign because it's just the distance, so it's a scalar. So the v with the arrow velocity is equal to the derivative of this displacement vector with respect to time. Lowercase t, remember, is time. And then acceleration is the derivative of that velocity with respect to time. Therefore, it's the second derivative of the displacement vector with respect to time. Remember, this is how we write a second derivative. Calculus is a prerequisite for this class. Now, in three dimensions, that force is going to have components, an x component, a y component, and a z component. The x component of the force is just mass times the x component of the acceleration. The y component of the force is mass times the y component of the acceleration. And the z component of the force is mass times the z component of the acceleration. So using the same substitution on the previous page, the x component of the force is equal to mass times the second derivative of the x position with respect to time. And the y component of force is mass times the second derivative of the y position with respect to time. And the z component of the force is mass times the second derivative of the z component of the z position with respect to time. Now remember, weight is proportional to mass. Lowercase w is weight for now. We're also going to use lowercase w for work, so pay attention to context. And this symbol alpha, it means proportional to in this context. And then lowercase m, of course, is mass. When you want to convert a proportion to an equal sign, you're going to use a proportionality constant. For gravity, that's going to be lowercase g. So this lowercase g is our proportionality constant due to gravity, and that converts our proportion to an equal sign. So g is the symbol for gravitational acceleration. And at Earth's surface, that would be 9.81 meters per second squared, which is the only kind of gravity we'll be doing in this class. It's not an astronomy class. Next would be units. There are different unit systems. For example, the MKS system, which is similar to the metric system. M in this case means the length is in meters. The lowercase k in this case means the mass is in kilograms. and the lowercase s in this context means the time is in seconds. Now, just like we had before, the force is equal to mass times acceleration. So 1 Newton, that's the units of force, is equal to 1 kilogram, that's the units of mass, times 1 meter per second squared. That'd be the units of acceleration. So capital N in this context is Newton, and lowercase k, lowercase g in this context is kilogram. Another unit system is the Cgs system. Lowercase c is not the speed of light now, it's of the length in centimeters. Lowercase g is not gravity in this context, it's the mass in grams. And the lowercase s in this context is still the time in seconds. So the units for force in the Cgs system is the dyne. So 1 dyne is equal to 1 gram times 1 centimeter per second squared. And you can convert the MKS system to Cgs system using 1 Newton is equal to 10 to the 5th power dynes. And then there's also the SI units, which is a modified MKS system. Now let's talk about pressure. Pressure is force over area. The symbol for pressure is capital P. The symbol for force is capital F. The symbol for area is capital A. Now, pressure, so P equals F over A. So remember, F, of course, is a vector. And then P and A are scalars. The units are pascals, capital P, lowercase a. 1 pascal is 1 Newton per meter squared. There are other units of pressure, though, such as atmospheres, torrs, PSI, which stands for pounds per square inch, where pounds per inch is squared, and then, of course, bars. So a lot of times you'll need to convert from one to the other. So 1 pascal is 1.98 times 10 to the negative 6 atmospheres, or 1.45 times 10 to the negative 4 pounds per square inch. 1 bar is 10 to the 5th pascals, or 0.987 atmospheres, or 750 torr. 1 atmosphere is 760 torr, and 1 millimeter mercury is the same as 1 torr. Remember, from chemistry, capital H, lowercase g is the symbol for mercury. Now let's talk about work. Let's say we're talking only about one dimension here. So the x dimension, positive x is to the right. We have this block here moving to the right. So it's moving in the positive x direction. The distance it's going to move is the dx. That's your instantaneous change in the position, or displacement in x. And then your force is going this way. So that's the x component of the force, because we're only doing one dimension. So that if lowercase w is work, then dw is infinitesimal work. For one dimension, the dwx is equal to fx dx. So this means the differential of the x component of work is equal to the x component of force times the differential of the position, x position. In 3 dimensions, you just sum them up. So you have the differential of work is equal to the x component of the force times the displacement in x, plus the y component of the force times the displacement in y, plus the z component of the force times the displacement in z. Now, that's just at one instantaneous position. If you're moving over, you keep moving, you add up the force over time. So the total work in one dimension is going to be the sum over all that time of the x component of the force with times the displacement in x. Now, the force can change over time, so we actually have to write it as a definite integral. So we have the definite integral from the x position, or at state 1, or the initial position, to the x position at state 2, which is the final position, of the x component of the force with respect to x. Now, if x is constant, then we can just pull it out and integrate, and we get work is equal to the x component of the force times x2 minus x1. That's the final position minus the initial position, or the change in position, basically. Now, what are the units in work? It's energy. Work is force times displacement. So we get joules equal to newtons times meters. 1 joule is equal to 1 newton times 1 meter, or just newton meters. And in MKS units, that would be 1 kilogram meter squared per second squared. You need to be able to convert all of these. In the Cgs system, you'll have 1 erg for energy is equal to 1 dyne. So dyne is the unit of force in the Cgs system, times 1 centimeter is equal to 1 gram centimeter squared per second squared. And of course you can convert 1 joule is equal to 10 to the 7th erg. Now power is the rate at which work is done. Power, capital P, which is the same as unit or the same symbol as pressure, but very different meanings, so you have to pay attention by context, is the derivative of work with respect to time. Lowercase w here is work, lowercase t is time. The units of power is work, so 1 watt is equal to 1 joule per second. Lowercase w is watt, capital J is joule, capital or lowercase s is second. Now let's talk about mechanical energy. Let's assume that we have a one particle system of any size for now. Work is equal to the integral from state 1 to state 2 of the x component of force with respect to x, plus the integral from state 1 to state 2 of the y component of force with respect to y, plus the integral from state 1 to 2 of the z component of force with respect to z. Now we want to substitute out for those forces. Remember that f of x, the x component of force, is equal to mass times the x component of acceleration, which is equal to mass times the derivative of the x component of velocity with respect to time. So that gives us, now these are two different variables. There's x and t. We need to convert. So this is how you do it. You have mass times the derivative of the x component of velocity with respect to x times the derivative of x with respect to time. Now we can substitute back in and say the x component of force is equal to mass times the x component of velocity times the derivative of the x component of velocity with respect to x. We've substituted in, remember lowercase v is velocity, so the x component of velocity is the derivative of x with respect to time. That's the substitution we made right there. Putting that back into the original equation, we get work is equal to the integral from state 1 to 2 of mass of the x component of velocity with respect to the x component of velocity, plus the integral from state 1 to state 2 of mass times the y component of velocity with respect to y component of velocity, plus the integral from state 1 to 2 of mass times the z component of velocity with respect to the z component of velocity. Now we're going to say, evaluating those integrals, we get work is equal to 1/2 mass times the x component of velocity at state 2 squared plus the y component of velocity at state 2 squared plus the z component of velocity at state 2 squared minus 1/2 mass times all this added up, the x component of velocity at state 1 squared plus the y component of velocity at state 1 squared plus the z component of velocity at state 1 squared. That's supposed to be a 1. So basically it's final minus initial. It's the difference. We're going to define k, the kinetic energy, that's a lowercase k, and remember when you have equal sign with 3 lines, that means always equal to, because we're defining it. So the kinetic energy is equal to 1/2 mass times the velocity squared. Using the Pythagorean theorem twice, we know that the velocity squared is just the x component of velocity squared plus the y component of velocity squared plus the z component of velocity squared. So we substituted in that for that. Now, only for a single particle system, work is going to be the kinetic energy at state 2 minus the kinetic energy at state 1. So remember, K2 is your final kinetic energy. K1 is your initial kinetic energy. So the subscript 2 here means state 2, and the subscript 1 here means state 1. So that basically means that work is equal to the kinetic energy at state 2 minus the kinetic energy at state 1, or just the change in kinetic energy. But that's only true for a one particle system. Okay, continuing on, we're in chapter 2, section 1 still. We're going to talk about different types of forces now. Now, one type of force is a conservative force. This is a force that is a function only of the particle's position. So we write that the force is equal to a function of x, y, and z if we're in Cartesian coordinates. Now, what's important about a conservative force is it allows energy to be stored. Now, examples of conservative forces are gravity, spring, or the electrical force, which is the Coulombic force. This is when charged particles get near each other, they attract or repel. Now, on the other hand, a force can be non-conservative. If a force is non-conservative, that just means that it depends on anything other than position. For example, it could depend on velocity or time. Now, we're not really going to be talking much about these, but examples would be friction, the tension on a cable, what's happening in your muscles, or when you're kicking a ball, etc. Now, if an object is moving, it has kinetic energy. Whether it's moving because of a conservative or non-conservative force is irrelevant. The formula is the same. Kinetic energy is equal to 1/2 mv squared. Now, you could show this as a vector because it's the velocity, but really, kinetic energy is a scalar. It's just an amount of energy. So you could leave the arrow off and it'd be speed squared, and you'd have 1/2 mass times the speed squared, and you'll get the number you want. But only conservative forces have formulas for potential energy. Now, PE, capital P, capital B, E can be potential energy. So, example, gravity, potential energy is just mass times gravitational acceleration times the height. Or for spring, the potential energy is 1/2 times the spring constant times the position squared. Or for the Coulombic force, the potential energy would be a constant times the charge of particle 1 times the charge of particle 2 divided by the distance between them. Now, actually, in this class, we're not going to use PE for potential energy, even though it makes sense, because we want one letter. Unfortunately, we're going to use capital V for potential energy because that's the standard. The reason that's unfortunate, of course, we're also going to use capital V for volume. So you always need to pay attention to the context of what you're looking at, so you know, okay, am I looking at the potential energy or am I looking at the volume here? Now, the derivative of potential energy with respect to x, that's the x component of the force. Notice the minus sign, I'll explain that in a minute. Likewise, the derivative of the potential energy with respect to y, that's the y component of the force. And the derivative of the potential energy with respect to z, that's the z component of the force. So the x component of the force, that's the force along the x-axis. So f sub y would be the force along the y-axis, and the f sub z would be the z component of the force along the z-axis. Now, the reason we have a minus sign is because our force and the displacement are in opposite directions. Now, work, we're going to say, remember, is the integral from state 1 to 2 of the x component of the force with respect to x, plus the integral from state 1 to 2 of the y component of the force with respect to y, plus the integral from state 1 to 2 of the z component of the force with respect to z. We want to substitute out those forces again. So what we have is work is equal to minus the integral from state 1 to 2 of the derivative of velocity with respect to x dx, minus the integral from state 1 to 2, the derivative of, potential energy. I screwed that up. I emphasize that. This is the derivative of potential energy with respect to x. Then minus the integrals from state 1 to state 2, the derivative of potential energy with respect to y, minus the integral from state 1 to 2 of the derivative of potential energy with respect to z, Now remember, the exact differential of potential energy then will be the derivative of the potential energy with respect to x dx plus the derivative of potential energy with respect to y dy plus the derivative of potential energy with respect to z dz. So substituting those in, we get work is equal to minus the integral from state 1 to state 2 of the derivative of potential energy. So we get minus the final potential energy minus initial potential energy. Distributing the minus sign, we get the initial potential energy minus the final potential energy, which is equal to the final kinetic energy minus the initial kinetic energy. So what that shows us is that for our single particle system, our one particle system, if you just move the 1s and 2s over to the same side, the kinetic energy in state 1 plus the potential energy in state 1 is equal to the kinetic energy in state 2 plus the potential energy in state 2. This is the law of conservation of mechanical energy, and this is only because of the assumptions we made using a one particle system. When we have more particles, it's going to be a little more complicated. So remember, this left side, the kinetic energy at state 1 plus the potential energy at state 1, that's the total energy of state 1. And we just call that capital E subscript 1. And then likewise, this right side, the kinetic energy at state 2 plus the potential energy at state 2, that's the total energy in state 2. And we're going to abbreviate that capital E lower subscript 2. Now remember, the kinetic energy is always 1/2 mv squared. When there's more than one, you add them all up. 1, 2, 3, etc. That's what this I means. The epsilon over I, you're adding up all the different I's. So you add up all the different mass velocity, and that's your total kinetic energy. And the same works for potential energy. Except, you're going to add up the particles in pairs. So you're going to add up the potential energy of particle 1 to 2, 1 to 3, 1 to 4, 1 to 5, etc., then 2 to 3, 2 to 4, 2 to 5. So you're going to add up all the particles I, and then all the particles greater than I, to compare to each other. The reason is because the potential energy from particle 3 to 4 is the same as the potential energy from 4 to 3, and we don't want to double count. So that's why we have this J greater than I in here. So this concludes Chapter 2, Section 1.